Last time we have learned that whenever a particle on a medium, for example like a string, starts to move, then the other particles on that medium or on the string will start to copy that. Okay, so as a result, it appears as if the pattern moves with time, right? Is this clear to you all? And when this pattern moves, that is what we call a wave, right? So it appears to us that there is some pattern, some shape that is moving, right? Remember, wave is not an object. There is nothing that is going towards the right side. I repeat, there is no physical object that is moving towards the right side. This motion is an illusion. Okay, but yes, definitely what happens is that as the energy travels forward, right? The energy travels forward through the string. That's how the pattern moves. Is it fine? That's what I have explained so far. Clear? So wave is a disturbance. Wave is a disturbance where energy is transferred from one point to another point. So the disturbance travels from one point to the other one. Okay. So we were talking about the types or classifications of waves, right? So therein we discussed, we mentioned mechanical waves, non-mechanical waves, right? So these are two ways to classify. Then further, there are two further ways to classify them. Okay, classify the waves. Listen to this carefully. One, transverse wave. Transverse wave. Okay, right? And second is longitudinal wave. So, what is a transverse wave and what is a longitudinal wave? You will be able to understand it very easily if you understand the meaning of these words. Transverse means across or perpendicular. Okay, actually perpendicular is not necessary in general context, but anyways, across or perpendicular. What does this mean? Have a look here. I'm going to explain in very simple way what a transverse wave is, right? So suppose you consider that string case again, let's say, and at the source you are holding the string and you move that point up and then you move it down and up and down. Okay, let's say. So what happens is that this source is going to oscillate in this direction, that is, let's say, in the y-axis. Clear or not? This source will oscillate in the y-axis, right, if you move it up and down. But the wave pattern that is formed, when you do this, the wave pattern that is formed travels towards the right side, that is, it travels along the x-axis. Clear or not? So the particle of the medium, the particle, not just one particle, all particles of medium oscillate or move in a direction perpendicular to the direction of propagation of wave. This is what makes transverse wave. Listen to this very carefully. Think of particle here, 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 anywhere. How is it going to move? It's not going to move horizontally. When wave comes over there, this particle will go up and then it will go down. Correct? That's what we were talking about yesterday. Right? And the direction of propagation of wave. Propagation means traveling. Propagation means traveling. So wave, that pattern, that shape which we are seeing is traveling in which direction? It's traveling in x direction. But the particles are moving in y direction. You understand what I'm saying? Particles, let's say P for particles, they are moving in y direction. But the wave is traveling in this direction. Clear? So this is what is transverse wave. Absolutely clear the meaning of transverse wave? Okay? Fine. Let's go to the other one, longitudinal. Now longitudinal means along the length. You know, the literal meaning of the English word longitudinal is along the length. Okay? So what's the proper definition or what's the proper condition for a longitudinal wave? So let's go to that. I'm erasing this list here. Okay? So two kinds of waves, mechanical, non-mechanical, and then two kinds of waves separately, transverse and longitudinal. Okay? Yeah. So what are longitudinal waves looking like? A longitudinal wave is where, suppose this is, let me just explain it with a very simple example. Have you seen the colorful or maybe steel toy called Slinky? It's like a big spring. Have you seen that toy? Have you ever played with it? Okay. Then hopefully you would be doing this with it, right? I'm sure you would have done that. And you would have noted that if one person holds it from this side and you would push this, suddenly let's say you give it a jerk and you push this, then have you noted that what happens is that these parts of this spring, it's basically a spring, right? These parts of the spring start moving back and forth like this. Have you noticed that? Yes or no? Right? Okay. So what is happening? Have a look at this. This is source. In your hand, you are having the source. That is the first point where the wave is going to start. Okay, so you give it a force. So this point will get displacement towards the right side. But because of that, it will push the next point towards right side. Then that will push the next point towards right side. And then they will all start oscillating like this. See, this is completely different from here. So here what is happening is that the parts of the medium, the parts of the particles of the medium, they oscillate in the same direction in which the wave travels. Did you understand? The wave will travel from the source to the other person. Clear or not clear? Okay? So this is completely different from here. So let's write the meaning. Particle of medium oscillate or move in a direction or in direction along the direction of propagation. Of wave. That is, they will move on the same line as the wave is traveling. Understood? Okay? So that's the difference between longitudinal wave and transverse wave, right? Now we can talk about some examples also. So this is definitely an example of transverse wave on a string. If you move the string up and down, this is going to make a transverse wave on this string, right? So that's one example. This is one example of longitudinal wave. clear that we see in nature, right? Another example of longitudinal wave is sound in air. When sound travels in air, it is a longitudinal wave. Alright? Okay or not okay? Along with this for longitudinal wave, I want you to relate this with two more terms that I am going to talk about here. Let's see. Do you realize, listen to this carefully, suppose that there is one particular portion over here, let's say, small portion, okay, I am showing it big, but think of it as a fairly small portion. So let's say it was like this. At some point of time, it's possible that the particles at the end point will both go, let's say, away from each other, like this and like this. So what will happen is that this portion will expand. Do you understand what I'm saying? If the particles at the end point both go away, do you realize that this portion will expand? Yes or no? Okay. Along with that, opposite to this thing. Suppose instead of going away from each other, they would come towards each other. Because see, they are oscillating like this, left, right, left, right, left, right. So it's possible that at some point of time, these two come towards each other. So do you realize that at that time this portion will get compressed? Because these two end points come close to each other, so it will get compressed. Clear or not clear? Okay. So what this means is in longitudinal waves, cause alternate compression and expansion. Which is sometimes also called rarefaction, not refraction, rarefaction. Okay, so longitudinal waves cause alternate compression and expansion of the medium. Okay, so what that means is some part of the spring will get compressed, some part of the spring will get elongated, some will get compressed, some will get elongated. Did you understand what we have written here? Okay. Alright then. So this is the basic intro of what are waves. Right? Probably you have learned all of this in 9th standard. Correct? Okay, so now let's go ahead with stuff. And you know that when we jump to a higher level, suddenly maths comes into the picture, right? So far we have not worried too much about the maths here, right? But now we will start with it. Okay. So let me make one thing very clear at the start. In this chapter, we are mostly, or rather almost going to focus on mechanical waves only. We will not be talking about non-mechanical waves. Okay, there is a separate chapter for non-mechanical waves, that is light and all that in 12th standard. Okay, that's when we will cover that portion. But it is very similar to what we are going to study in this chapter, right? Okay, so anyone thinking, okay, this 11th not important, you'll have a bad time in 12th then. So stay focused. Everything used in this chapter will come over there in some form or the other, right? Okay. So mostly, like I said, mechanical waves, and even then, we will really be understanding concepts using transverse waves. We will not go too much into longitudinal waves, equations and all that. I repeat, all the maths that we are going to understand about waves, it will be about transverse waves. Okay? Does it mean it's not applicable to longitudinal waves? No, it is applicable. I repeat, it is applicable equally, right, with some minor changes, right? But there is no need to do both for transverse and for longitudinal separately. There is no real need. If you understand the physics behind transverse waves, then the physics for longitudinal waves is almost the same, right? Okay. Now, first thing, wave pulse and wave train. Okay, strange looking title here, wave pulse and wave train. So what's wave pulse? Wave pulse means a disturbance occurs for a short time and then it stops. Let me give you an example. Here is a string. Okay, let's say it's tied somewhere so it maintains its position. You take this end in your hand and you jerk it only once and then stop. You understood what I said? You take the source, you take this point up and down and then that's it. You stop. You don't do anything else. Clear? So from here you are going to start a wave. But this is a wave pulse. Wave pulse basically means a single disturbance which is for a short time. Understood? Clear? So after some time, what are you going to see? Again, like I was drawing earlier, this wave pulse will travel here, this wave pulse will travel here, this wave pulse will travel here like this. Is it clear? Okay or not okay? Sahil, can you see it later from the recording? Okay, there is not much I can do now about it. Okay, so this is what we have got for a wave pulse. So what this means is that there is a single disturbance and the disturbance is traveling. That's called a wave. But now what's a wave train? Generally, train is something that refers to lots of elements one after the other. Correct? That's called a train. So wave train means, let's say here is a wall and a string is attached to it. You hold the string in your hand or the rope in your hand and then you start moving this, but you continue moving this for a long time. You understand what I'm saying? So because of that, what will happen is that at first it will not look different from wave pulse, right? At first it will just be like this. But then you don't stop. Your hand is still here and you are going to move this. Now you move the source down. Now you move the source down. So as this proceeds, see the pattern moves forward. The wave propagates in this direction. Okay, but now we are moving the source down, so the string will become like this. Is that clear? Yes or no? Then what will happen next? You are still not going to stop. Let's say you moved it up, okay, then you moved it down, and then now you move it back up again. So now it will look something like this. By that time, this pattern has already traveled forward. You understand what I'm saying? This pattern keeps traveling forward, okay, like this. I'm sorry, this is extremely horrible drawing on my part, but fine. Right? So this is how the pattern starts to move. While you are doing this, the pattern starts to move towards the right side. Further, you don't stop again, you move the source down, so that will create something like this. Okay, so the pattern is still moving. Understood what's a wave train? Is it clear what is a wave train? So what's the difference between wave pulse and wave train? Just one thing. If there are wave pulses one after the other, right, continuously, one after the other, then that makes a wave train. Clear or not clear? Clear or not clear? Okay. Right? So normally what people call a wave is this shape. Right? Correct? People call this shape a wave. But the truth is, listen to this. This shape is not the wave. This shape is not the wave. Right? This is the shape of the string. For example, here we are talking about the string. This is the shape of that string. But the phenomena that the energy is traveling forward, and with that the pattern also appears to move forward. The pattern you can see gradually appears to move forward. That phenomena is called wave. Again, wave is not this picture. Remember, right? Wave is the process that this disturbance is moving forward. Clear or not clear? So this is wave pulse, and if you do it continuously, it's a wave train. Now, let's talk about wave speed. Okay, let's talk about wave speed. Now, what is meaning of wave speed? It means the speed with which disturbance travels in the medium. Again, wave is not an actual object, remember. So it's not like, okay, what's the speed of car? That's wrong. Okay, wave is not like a car. Wave is a phenomena. So wave speed means speed with which disturbance travels in the medium. So let me give you a simple example. Do you remember that I told you earlier that whenever a wave is created, every particle tries to copy the source? Yes or no? Every particle tries to copy the source. Do you remember that? Yes, no? Yeah, okay, fine, right? It's a very important sentence, by the way. It might look so childish, right? So simple, but it's very useful. So let's say that at time t equal to 0. Okay, at time t equal to 0, suddenly we move this up and the shape of the string becomes like this. Okay, so source is here. That is, what have you done? You will be holding this in your hand and you pulled it up and let it go. Okay, you understood that? At time t equal to 0, suddenly we do this, right? Let's say this is origin. Generally we take the source as origin, x equal to 0. Positive x on the right side, okay, negative x on the left side. So suppose you want to know when will this particle over here, let's call it p, which is at x coordinate x. Did you understand what I have marked? This particle p is at x equal to x. Then when will this particle be in the same position or in the same situation as the source is? So at that time, do you realize the picture will be something like this? Yes or no? Do you realize the picture will be something like this? Okay. So what is wave speed? Wave speed means whatever distance this disturbance or this pattern see, pattern was created here at t equal to 0. In some time, let's say t equal to t, it reaches here at x equal to x. Do you understand what I'm saying? Then the wave speed will definitely be x upon t. Understood? Understood or not? Again, what that means is that this disturbance that you created here, it is moving towards the right side. And we see that in a time interval 0 to t, that is t, it travels a displacement or a distance x along this medium. Clear? This is clear or not? When you move this up, it will move the source particle upwards, correct? So it creates a pattern on the string, this kind of shape, right? Then even if you put it down, this pattern will travel forward. That's how wave travels, or that's how a disturbance travels, right? So this pattern, when it reaches here, obviously, I hope you see that this is the same pattern, right? Okay, so it takes a time t, and then the wave speed would be x upon. Clear? Okay. What this means is, if I put all this concept in a slightly different way, it is, I can say that if wave speed is v, then a particle at distance x from the source, if wave speed is v, then a particle at a distance x from the source is in same situation as, at t equal to x by v, as source was at t equal to 0. It might take a little bit of time to understand what's going on here, because we are talking about two different particles at two different points of time. So what have we written here? We are saying that the situation of this particle P, at which position at x equal to x, and at what time at t equal to x by v, is same. This situation is same as the source at which time. Clear or not clear? Devers, I am going to ask you a counter question. Do you know what is wave phase? Do you know what is wave phase? Explain what is wave phase. Then why did you put that question over there? Come on, Devar. If you don't know what you are asking, why are you asking that? Okay, so getting back to this, someone also asked how, or Arkan, I don't understand what's the meaning of question how. What do you mean by how? The wave travels, so this pattern moves. So we are comparing the situation of P with this. Okay, basically both are moving up. So how much has this moved up? Let's say y. Then this would also have moved up y. Is that clear? That's what we have written here. Is that clear or not clear? at one thing. They are trying to copy the source. Right? They are all trying to copy the source. So do you realize that different particles will be showing the same behavior as source was showing at t equal to 0 at different times? Different particles will show the same behavior as source was showing at t equal to 0 at different times. For example, let's think of some other points on this string. Let's say A, B, here's P, and here is suppose Q. Then do you realize that A will come first in the same situation as source was at t equal to 0, right? So situation of source or motion of source, displacement of source, velocity of source, acceleration of source at t equal to 0 will be same as that of A at time t equal to x1 upon p. Did you understand this? Situation of source, that is everything about source, displacement, velocity, acceleration, okay, will be same as that of A at how much time? x1 by v. Why so? Why so? Because in that much time, that is x1 upon v, where will this disturbance reach? It will move forward, 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 and in that much time it will reach here. Do you understand what I am saying? Yes or no? Why? Because wave speed is v. So, how much time does it take to travel a distance x1? It will take a time t equal to x1 by v. Clear? So, in that much time, t equal to x1 by v, from here the disturbance will move and reach A, such that whatever S was doing at that point, now A will be doing. Similarly, I can say that B would be doing this at some time t equal to x2 by v if this distance is x2. Clear or not clear? Clear or not clear? Okay. Now, simple question. Who gets to copy the source first? Out of all these points that we have marked, who gets to copy the source first? Very good. A, well done. So first of all, the wave is going to reach A. So A will start its motion and it will start copying source the first, right? Before all these points. Then there will be B, then it will be P, then it will be Q. Clear? Alright? So do you realize, listen to this carefully, do you realize that all of them are going to do same motion, same type of motion? They'll move with some velocity, they'll go up and then down and all that. Whatever they do, they are all going to do the same. But they do it at different times, yes or no? They are all going to do the same, but they will do it at different times. Clear or not clear? Okay. Right. So that's the importance of velocity or wave speed, or wave velocity. It tells you that if there is some source here, then in how much time this particle P will copy that source. Clear or not clear? Right? Okay? So please remember the meaning of wave speed and its importance here. Right? Okay, so obviously you can realize that if the wave speed is more, this disturbance will travel fast. Right? So the gap of time from here to here, for the disturbance to go from here to here, will be less. it means the other points will copy the source quickly. Is that clear? The other points will copy the source quickly, right? If wave speed is more. If wave speed is less, they will copy it after a little bit more time. Okay, that is the disturbance travels slowly, right? Okay, so that's about wave speed. We'll definitely be coming back to all this, right? Okay, this was just a conceptual understanding with a little bit of maths, right? Okay. Now, the next thing. Frequency of wave. Okay, frequency of wave. Now, this frequency is typically only going to make sense if the particle, the source where the wave starts, is doing some kind of periodic motion. I'll tell you what, have a look. If this particle, listen to this carefully, if this particle goes up and then goes down, that's it, okay, and comes back to this position, okay, where the string is lengthened, then it would not have any kind of frequency. Do you realize what I am saying? Yes or no? Because frequency is only there for what? For periodic motion. Do you remember that only periodic motion can have frequency? Correct or not? Okay. So instead of just considering a single wave pulse where the particle goes up and down, we will now start talking about wave train. So let's say that source is doing simple harmonic motion. Okay, let's say the source is doing simple harmonic motion. Then we call the wave simple harmonic. Okay, what do we call it? Simple harmonic, not SHM but just SH, simple harmonic wave. Okay, so what is the meaning of simple harmonic wave? When the source is doing SHM, the wave that is created, that will be simple harmonic. Alright? Why so? Let's see. Think about it. Here's the string. Okay. This is source. Alright? Here's the source. Now, if source is doing SHM, then all particles are going to copy the source. Yes or no? Is that clear? If source is doing SHM, all particles are going to copy the source. Clear? What does that mean? Every particle on this string will be doing simple harmonic motion after some time, of course. Correct? That is, if you keep moving this up and down, that is oscillating. Let's say this keeps oscillating. This is doing simple harmonic motion. So after some time, the second particle will start oscillating. After some time, third particle will start oscillating. Fourth, fifth, like that. Everything will start oscillating. Is that clear? And they all will be doing SHM. That's why this is called a simple harmonic. Right? So if the source is doing simple harmonic motion, all particles on the string or on the medium will start doing simple harmonic motion. Understood? Okay. So this is where frequency comes into the picture. Right? This is where frequency comes into the picture. Because in simple harmonic motion, source will definitely have frequency, right? So you can say let Fs be source frequency. What does that mean? It is the frequency with which the source is oscillating. It is the frequency with which the source is oscillating. Right? Then, suppose here is a point P, anyway, at some distance. Then do you realize that because P will try to copy the source, will also be equal to Fs. Yes or no? That is, if source is making two oscillations, let's say for example, in 1 second. Let's say source is making two oscillations in 1 second. That is, in 1 second going up and down twice, right? So like this. So then when P will copy it, it will also do the same. Okay. But what about Q then? What do you think Q will be doing? Will it oscillate 2 times in 1 second or less times in 1 second? What do you think? Will Q oscillate 2 times in 1 second or less than that? Yes, 2 times, because they are all going to copy whatever the source is doing. So, if source has some frequency Fs, then that means every particle which receives the wave or disturbance, every particle which receives the wave or disturbance will have same frequency. How much frequency? Fx. Did you understand? All the particles will have same frequency as the source. Clear? Okay. Right. Now, one simple thing. This is frequency of wave. But here we are talking about frequency of particles, right? The source, point P, point Q and all that. Right? So, are these two different? Well, the answer is the name is different, but the meaning is same. Let's see how. In lower classes, I am sure you have been taught that frequency of wave means number of waves passing through a point in 1 second. Is that what you have been taught? Number of waves that pass through one point in 1 second. That is called frequency of the wave. Right? So that only if you remember from that. Okay, otherwise it's just fine. So if this is the frequency of the wave, then how is that related with this? Let's see. Very simple idea. If here is one point P, let's say, okay, and you are observing this point closely, you are going to see how many waves pass through that point P in 1 second, right? So suppose the source is having a frequency, let's say 2 Hz. Suppose the source has frequency 2 Hz, let's say. That means in 1 second it will oscillate, it will complete 2 oscillations, 1 and twice. So do you realize that after 1 second of starting the motion, let's say first source went up and then it went down, we would already have this much created on the screen. Yes or no? Is this clear? Yes or no? I hope you are noticing what I have drawn. Source went up, source went down, 1 oscillation complete, then up and down, 1 oscillation complete. So like that there are 2 oscillations. So do you realize that every second on this string, 2 such wave patterns will be generated. Correct or not? On this string, every 1 second, 2 such patterns will be generated. Correct? Yes or no? Okay, so after 1 more second, what would happen is that this pattern would already have traveled forward, right? So now we would have it 2, 3 and 4 like this. Is it clear? So do you realize that wherever the point P is, anywhere on the medium, no problem, every 1 second, okay, in an interval of 1 second always, 2 waves are going to pass through it. Yes or no? Did you understand that in 1 second, 2 waves are going through the point P? Clear or not clear? Because, why so? Because every second 2 waves are generated and they are pushed through, right? So if at some time the wave just reaches here, then 1 second later, it would be as if that 2 waves have passed through the point P. Okay, diagram again not to the scale as it should be, but anyway. You understand what I'm saying? Why is it like that? Once again, it's because the source is generating 2 waves and it is throwing them in 1 second. So wherever the point is, you are going to get 2 waves going through that point in 1 second. It's fairly simple. Listen to this carefully. Let's say balls could float. Okay, suppose there is no gravity, right? And you are standing here. You are the source, and here is your friend, and your friend is watching by. Suppose there is no gravity, and you throw 3 balls in 1 second. Okay, back to back like a machine. Okay. So do you realize that 3 balls will also pass through or pass next to your friend in 1 second? If you are throwing 3 in 1 second, 3 balls will also pass through your next to your friend in 1 second. Correct or not? Okay, so that's the idea here. So final punchline of this topic, it is that if the frequency of source is Fs, just like you are throwing 3 balls per second, then any other point on this medium also receives same. In short, what this means is that frequency of wave is always equal to frequency of source. Very important but very easy thing to understand. Okay, frequency of wave is same as frequency of source. Yes, you are right, Vishwa. Frequency never changes in a wave train. Okay, frequency never changes in a wave train. Okay, source decides frequency. Just write that. Source controls or decides frequency of wave. Okay, this is also a very useful sentence. Okay, I want everyone to remember this also. Source controls or decides frequency of wave. Okay, and frequency of wave is always equal to frequency of source. That's it for this class. See you all in the evening. Goodbye.